A lot of things spin, from objects to machines to this record player, the earth, and even people. So it's likely you've had some experience spinning before, and if you've ever had the experience of being in a car that takes a curve, or maybe being on a merry-go-round that's spinning around, you've likely had the experience where it feels like you're getting forced or pushed towards the outside of the circle. But it turns out that that force is, it's actually kind of fake.
He's a fake! He's a fake!
How can a force be fake? Well, in this video, we're going to take a look at centripetal motion or circular motion and how it gives the apparent feeling of a force towards the outside of the circle. So let's take a look at understanding centripetal motion. Okay, so to understand circular motion and centripetal motion, we're going to imagine a merry-go-round. So a person on this merry-go-round spinning around in a direction. Let's look at this from a top view, the person being the circle spinning around like this. And we know that their motion would be described as spinning around clockwise like this. But I want to consider right at the bottom there, what direction would we say they're moving? At that moment in time, I know they're going to go around later, but in that moment of time, they would actually be described as moving tangent to the circle, which is directly to the left. At that moment, their velocity would be going directly to the left. Later on, it would be directly up, later on to the right, and so on and so forth. But at that moment, they'd be moving directly to the right, tangent to the circle. Why is that important? Well, let's consider at that location if they let go of the merry-go-round and there's no friction acting on their feet, what would happen to this person? Well, the person would continue to move in a straight line in that direction. That's actually Newton's first law of inertia. An object in motion stays in motion as long as it's not applied by any other forces. So we get rid of all the forces, we let go, and we keep moving in that direction. Okay, well, what if you didn't want to fall off the merry-go-round? That'd be a bad result, but you want to stay on. You feel yourself moving off. What would you have to do? Well, you'd have to pull yourself back on. You'd have to apply a force to the center of the circle to pull yourself back towards the middle of the circle. Okay, let's say you get back on and you're good here up until that point, but then again here, if you let go, you would be traveling in the upwards direction, tangent to the curve, and you would go off of the merry-go-round in that direction. So what I'm trying to get to is that as it's spinning the entire time, you have to be pulling yourself towards the center so that you stay on the merry-go-round, and that's called centripetal force. You have to keep applying a force to the center of the circle to keep something going around in a circle the entire time. If you ever let go, you're going to be flying off in a straight line. So centripetal force is the focus of this lesson and is what we're going to be working at calculating. A reminder, it's a force towards the center of the circle to keep something going in a circle. So what about this fake force I was talking about? Well, let's imagine we have 4 people or even just 4 objects on a spinning circle. If I spin the circle, it looks like they move to the outside, and they do move towards the outside of the circle. It appears that there's a force pushing them there until we realize there's actually no force pushing them there. It's actually the absence of forces. So just like I talked about letting go of the merry-go-round before, if all of these objects are spinning around, this shows their velocities, the direction that their velocity would be showing. Okay, and if there was nothing holding them on, instead of being pushed to the outside, with the absence of forces, nothing holding them on, no forces, they would just travel in a straight line, which is towards the outside of the circle. So this is called the centrifugal force. It's kind of fictitious or kind of fake force because it's actually what happens when there's no forces going on. You just keep traveling in the initial direction that you were, which is towards the outside of the circle. So let's sum that up with some notes here. We have the centripetal force, a force applied towards the center to keep an object going in circular motion. The centrifugal force, a fictitious force experienced by a mass in circular motion as it travels in a straight line towards the outside of the circle. So just to show that centrifugal force here, you can see if I have a cup of coffee beans and we spin it around, the coffee beans look like they get force to the outside, but that's again just because there's nothing pushing them towards the inside or to keep them in a circle. There's no centripetal force. Okay, so I hope that's making sense. all the calculations will be centripetal force, the force towards the inside. So let's focus on that and try and get some calculations for how we do that. So to look for some formulas to calculate this, we're going to look at the force required to stay in a circle. We have one equation of force from before that was F is equal to ma. Force is equal to mass times acceleration. But that might seem a bit confusing because when we're spinning in a circle, you could speed up or slow down, but usually the speed stays pretty much the same. We start at 2 meters per second and stay at 2 meters per second the whole time in this example. So it doesn't really look like there's any acceleration going on here. It looks like it's more of a constant speed. But to look at this closer, we have to actually look at what acceleration actually means. This definition is a change in velocity. But still, that doesn't really help us. We look at this, it still looks like 2 the same time. It doesn't really look like our velocity is changing until we remember that velocity is a vector. A vector means we have to take direction into account, not just how fast you're going, but what direction you're going. And I haven't done that on that picture here because 2 meters per second to the left or 2 meters per second up is different. So I'm going to break it in how fast we're going in X side to side and how fast we're going up and down, which I'm going to call Y. So it looks like a lot, but let's take a look at these velocities. So grab my pen, we're going to go to the bottom here. So initially, we're going in X 2 meters per second to the left. So I'm going to call that negative 2 meters per second. Nothing up and down for this location right here. Remember that arrow pointing directly to the left. Nothing up and down. Now we go over here, the velocity is directly upwards. So there's plus 2 in Y, but no motion side to side in X. And then over here in this location, we got 2 meters per second to the right, nothing up and down. And in this location here, going down, negative 2 meters per second in Y, 0 meters per second in X. Okay, so when we look at the directions is changing a lot, which means since velocity takes direction into account, the velocity is changing. Even though the speed's the same, 2 meters per second, when we take into account direction, our velocity is going to be changing. Okay, so that is a change in velocity. Therefore, by definition, that is an acceleration. Even though we're at 2 meters per second, because we're changing our direction, that is called acceleration. It's a bit of a different acceleration than just in a straight line speeding up. So we're actually going to give it a different term up here, AC, which is centripetal acceleration or acceleration centripetal. So to calculate centripetal acceleration, we're going to have to apply a centripetal force, FC, or to get centripetal acceleration, we need a centripetal force. So this is the main part of the formula. Let's expand it a little bit. So here's what I wrote from the previous one, but we need to figure out how we would get that centripetal acceleration. It's not the same formulas that we use in kinematics. How we're going to solve for it is v squared over r. V squared over r, how fast you're going divided by the radius of the curve that you're traveling there. Now, I don't really love that there is a v there. The v is correct because it's talking about how fast you're going at that moment. It's going to be the acceleration required at that moment. But understandable that when we're going around in a circle, we're not going to have to put in like plus or minus for that number. We're just talking about how fast we're going. Probably sounds a bit confusing, but basically how I'd sum it up is you're basically going to input the speed in that place for velocity. Okay, just how fast we're going at a specific moment in time. In that previous example, 2 meters per second. Divide by the radius, and we would get a AC. So the last thing to do is just combine these formulas, or I could get a formula for centripetal force is m times v squared over r. So these are the new formulas for today. FC is MAC. Since AC is v squared over r, they combine to be FC is mv squared over r. I've thrown the formulas at you, but let's take a look at how we're going to use them. So let's look at this first example. A 60-gram tennis ball is swung in an 80 centimeter or on an 80 centimeter string, and it completes 3 circles in 3.5 seconds. What's the centripetal acceleration? Okay, well, we have a formula for centripetal acceleration. AC is equal to v squared over r. Okay, hopefully you can see in that animation when it was spinning around, it was spinning around that 80 centimeter string. So the radius of that circle is actually the length of the string. We can just put 80 centimeters or 0.8 meters in for our radius. But it gets a little bit trickier when I look at velocity because the question didn't tell me anything about velocity. How could I figure that out? What it did tell me is it told me how long it takes to complete 3 circles. So what I'm actually going to use here is that v is equal to d over t, and then I can solve for how fast it did that circle. Let's take a look at that more closely. So as it's going around a circle, this is the path that we're going to follow. Okay, so following that path divided by how much time should give us the velocity, how fast we're going, assuming it's going at the same speed the whole time. Okay, how do I find the length of that path? Well, it's the circumference, which is 2 pi r. That's the circumference, or the distance around the outside of the circle. So if I take that and put it into v is equal to d over t and put in my circumference, 2 pi 0.8, you might have noticed I also put a 3 right here next to me because it went 3 circles. So I did 2 pi r, the circumference, 3 times, so 2 pi r times 3, and then divide by the time, 3.5 seconds. And I get an answer there of 4.308 meters per second as its velocity. Okay, so now that we know how fast it's going, let's just throw that up into the equation. Don't forget to square it, so 4.308 squared divided by 0.8, and I get an answer of 23 meters per second squared for our centripetal acceleration. Now, it could go one step further. I've changed the question here to what's the centripetal force. If it asked me this right away, I'd have to use mv squared over r. But since I already have that AC, it's actually not too bad a question. I'm just going to say Fc is equal to mac times our mass by our acceleration, 23 point, use your decimals there, and I get an answer of 1.4 newtons. Okay, a theory question could come up and say, what direction is that force? Always to the center of the circle. So that 1.4 newtons, if I'm swinging around that tennis ball, I have to keep pulling the tennis ball to the center of the circle for the entire time that it's going in that circle. I'm going to finish this video with a harder question. This question says, a person on a merry-go-round swing is traveling in a circle of 8.0 meters, that's the radius. If the swing makes an angle of 15 degrees from vertical, what speed is the merry-go-round going? Okay, so this scenario a little bit difficult. We're not just swinging around horizontally like the tennis ball, but it's hanging at an angle. So let's show that here with the mass hanging at an angle, and that's the direction that the swing is going to be pulling the person in. And we know that's going to be 15 degrees. Might be a little bit hard to know how to start this question, but where I'm going to begin with is the reason that we're hanging down at an angle is because something's pulling it down, and what's pulling it down is going to be gravity. Gravity is pulling it down in this direction. So this is starting to look kind of similar to what we covered in equilibrium questions. If you need a recap of that, I'll put a link here. But what that kind of is showing that there's going to be multiple forces pulling against each other and some of them equaling out. That was what equilibrium was. So Fg is pulling down, the string has to be pulling equally up to stop it from falling. Okay, now at this point, if it's similar to an equilibrium question, we might be thinking, well, then there's going to be a force going this way, and that's going to be balanced out by what the string's pulling back at. And I might think, okay, well, that's going to be the centripetal force swinging it around, so I'm going to label that Fc. However, when you draw that on the diagram, you realize I just drew Fc towards the outside of the circle. Fc is always supposed to be towards the inside. So there's actually nothing pushing it towards the outside. Well, then at that point we say, well, this isn't going to be in equilibrium because this is pulling it in. If nothing's pulling it out or pushing it out, this isn't in equilibrium. And you're exactly right. It's not in equilibrium, which means it's accelerating. It is accelerating because it's going in a circle. So going in the circle isn't where all the forces are balanced. It's where there is a net force pulling it in to make sure that it goes in a circle. So there is no force pushed to the outside. It's just a force pulling it back in so it doesn't just shoot off in a straight line. So to put that more formally, I'm going to put Fc here. That's required to keep it going in the circle. Okay. At this point, we've actually solved most of the problem. It probably doesn't seem that way because we haven't put any numbers, but this is the big key to this question. Fc is what I got to pull in with, and then I got to balance out gravity. So that's what the string is doing. It's providing the Fc I need to go in a circle, and it's countering out gravity. After this, it says, well, I have this side of the circle is Fc, this side of the triangle is Fc, and this blue side is going to be Fg. I have an angle relating those two. It's 15 degrees. Opposite and adjacent 15 degrees, tan 15 is equal to Fc over Fg. So I'm going to put that in there, but I'm going to put the formulas for those two. So tan 15 is equal to mv squared over r, that's Fc, over mg. That's going to be my adjacent side. At this point, you might be thinking, that's a lot of m's. How am I going to solve this since I wasn't even told the mass of the person? This is where we notice it's mv squared over r divided by mg. There's an m in both of those. M divided by m cancels. We can get rid of that mass. And at this point, we just got to rearrange for velocity. So I'm going to times that g over. So tan 15 times g is equal to v squared over r. Now I'm going to times the r over, take the square root, and we're set up to solve for velocity. So tan 15 times g, which is 9.81, times the radius, which is 8. It told us that's the radius of the circle. And we get an answer. Make sure you do take the square root of 4.6 meters per second is how fast it's swinging. And that's all we got for this video. So thank you so much for watching. I hope that helped you to understand the difference between centrifugal and centripetal force, and then understand how to do calculations with centripetal force. If you're looking for more instructional videos on physics at the high school level, check out our playlist. Thank you so much for watching again, and I will see you in the next video.
He's a fake! He's a fake! He's a fake!